This morning we have 4 speakers. I'm the first one. And I'm Baodong Liu from Beijing. And it seems that everyone knows. And today my topic is why uncertainty theory is useful. Perhaps your first question is what is uncertainty? Or what is uncertainty theory? Anyway, no matter what it is, I need this one. No matter what it is, uncertainty is not a probability. If so, I will say why probability is useful. And second, uncertainty is not fuzzy. Otherwise, my title should be why fuzzy is useful. So, uncertainty is something that is different from probability, also different from fuzziness. So it's some new things. Now, in order to make it clear, usually we say we are in the state of indeterminacy. That is, in many cases, we don't know the future, what will happen. For example, here, when we toss a dice, we don't know which face will appear before we toss it. And for example, this is this one, remote control, and we don't know its lifetime, right? We don't know. And also, some people buy stock, and usually we want to know what this stock price is. I mean tomorrow. If you know it, then you will become rich and rich. Perhaps, did you buy stock before? Maybe. But anyway, we want to know the stock price tomorrow, but we don't know. And this means for this phenomena, we will create indeterminacy. And usually, we want to model indeterminacy. We have many approaches. For example, the first one is probability. That was invented by Professor Kermoglu in 1933. And the second one is fuzzy set. And that was invented by Professor Zadar in 1965. And the third one is uncertainty. I will introduce it today. And now we have many methods. And how do we use it? And or how to use it? This is the main problem. Let's say. Now, for example, we want to know the stock price tomorrow. So, but we don't know it. How to do? We may say what the stock price is today. For example, today is $10. And then we may check the stock price yesterday. For example, $9. And then the day before yesterday, for example, $11. And then the price and the price and the price, and then we may have a sequence of stock prices. Now, we suppose that we have 100 days. 100. We may observe the 100 days, and then we may get 100 data. And then next step, we will count how many days the stock price is less than $10. For example, 20 days, and then 20 days is divided by 100. That is 0.2. And then we should have a bar. This form. Here is $10. We have a bar. And the height of the bar is 0.2. And then how many days the stock price is less than $11? For example, totally 30. And then 30 divided by 100. And we got 0.3. And then we have a bar. And the height of this bar is 0.3. and then how many days is less than 12, how many days is less than 13, and so on. And then we got a graph, this one, and we call it histogram. And then next step, we will find a red curve, such that the red curve is as close as possible to the frequency. And in this case, we will call the red curve as probability distribution. And based on such a distribution function, we have no choice but use the probability theory, and from which we may get the mean value, we may get the variance, we may get the moments, and so on. And in this case, you have no choice but use probability theory, because probability theory is the best one. It is better than fuzzy set. It is better than uncertainty. No choice. But here, if we have samples enough, then we may get the probability distribution, and then we may use the probability theory. And in many cases, we have no data. That is, we have no observations. And if we have no it, then we don't know the frequency. We don't know. And in this case, we have invited some expert to give some evaluation on it. For example, now I have here is for example a new stock, and we know observations, and then I may ask you, how likely the stock price is less than $10? And for example, in this case, you may say, and your answer is 0.2. And then here is $10. And as an expert, you may think that the belief degree, this stock is less than $10 is 0.2. And then you may get the belief degree that this stock price is less than $11. And then we have a red curve. In this case, the red curve is not probability distribution. It's a belief degree. And usually, we know that human beings usually overweight unlikely events. That is, here, the stock price is less than $10. It's impossible. But as our human beings, we usually think it's possible. For example, 0.2. And this conclusion is not made by me. It was proposed by Professor Kahneman. Kahneman is a Nobel Prize winner in economics, and he published a paper in 1979. And he said, human beings usually overweight unlikely events. That is, we make our belief degree, and usually the variance of the belief degree is much greater than the variance of the frequency. And in this case, probability theory is no longer valid. And if you regard the red curve as probability distribution, then it will get wrong results. Now, that is two cases. First one is, if we have samples enough, then we may get the probability distribution. And in this case, we have no choice but use probability theory. And if we have no samples, then we should invite some expert to give some belief degrees. And in this case, we have no choice but use uncertainty theory. Next one is, I would like to conclude that for modeling indeterminates, there exist two mathematical systems. One is probability, another is uncertainty. Agree me or not? Yeah. Personally, I think maybe all of you don't agree with me. Because some people think that probability theory is unique. That is the only reasonable method. And some people think that everything is probability. And there's nothing others. For example, and in for some mathematicians, probability is the unique one. Fuzziness, nothing. Uncertainty, nothing. And also for all of us, we think that now you say we have two mathematical systems. One is probability, another is uncertainty. Where is fuzziness? Do you think so? And now I will explain why I get such a conclusion. Now, let's see. And here is a bridge example. Let's see. And here is a tank. We may suppose that the weight of the tank is 90 tons. Exactly, 90 tons. And for each bridge, and the strength is usually unknown. And for this case, we suppose that, for example, in Korea, we have 50 bridges. And for the 50 bridges, the worst one is 98. And the best one is 102. Perhaps you want to know, how do you know that? Yesterday, God told me. It's like this. And now, we have 50 bridges. And we don't know its strength. And God told me that the worst one is 98. The best one is 102. And now, we don't know it. And then we may invite some expert, maybe give us some evaluation. For example, they may tell you, the strength of the bridge is less than 90. The belief degree is 0.2. And the strength is less than, for example, 95. And the belief degree is 0.3, and then so on. But anyway, the expert may give belief degree like the red curves. And now, in the real case, now we may have the tank cross over the 50 bridges. And the first one, no, we have a tank. And then the tank will cross over the first bridge. Because, the strength of the bridge is 98. And 98 is greater than 90. This means the tank may cross over the first bridge 100%. Right? The tank may cross over the first bridge 100%. Yeah. And then second bridge, because the worst one is 98, and 98 is greater than 90. That means the tank may cross over the second bridge 100%. And then the third one. And then the last one. That is, the tank can cross over the 50 bridges with probability 1, 100%. Absolutely. Now, if we think that the belief degree is a probability distribution, let's say what will happen. Now, here, if we think the red curve is a probability distribution, then the probability that the strength is less than 90 is 0.2, and is greater than 90 is 0.8. Now, let's have the tank cross over the first bridge. What's the probability that the tank may cross over the first one? 0.8. And the second one, also 0.8. And what is the probability that the tank may cross over the first two bridges? That is 0.8 times 0.8. It is 0.64. And then the third one times 0.8. And then totally 50. That is, the probability is 0.8 times 0.8 times 0.8, 50 times. What is it? Almost zero, right? It's zero. It's zero. That is, if we think that all the things we don't know are probability, then it will be a mistake. From this example, we may say that we can't deal with belief degree by probability. So, probability is not unique. And we need some method different from probability. And from this example, and we may think that probability is not unique, so we need other methods. And second, we don't know the strings. Then most people think that they are fuzzy. And if we think it's fuzzy, then we may have a membership function. Anyway, we may have a membership function. And we may suppose that the membership function takes the value 1 at 100. And don't argue with me why I select such a membership function. It's not the focus of debate. And now, if we think the membership function of the strings is this one, then from a fuzzy theory, we may go the first conclusion. The conclusion is the strings is exactly 100 with possibility measure 1. Here, we have a membership function. Then we may get a conclusion. The strings is exactly 100. Not less, not more. Not 100 plus a feather. Not 100 minus feather. And the possibility is 1. Do you believe? And you believe the first conclusion? I did a lot of survey. No people agree with it. Because it's impossible. Just like, what is the length of this one? You may get any membership function. And we may find the point at which the possibility degree is 1. And then you think that, for example, it's just 10 centimeter. Just like this case. And do you think the strength of the bridge is just exactly 100? Maybe, at least for me, I don't believe it before I become crazy. So, I did a lot of survey. And all the people don't agree with this conclusion. That is, this conclusion is inconsistent with our, with our thinking. And our mind does not like this. Second, and also from the fuzzy theory, we may get such a conclusion. That is, this strength is not 100, no matter what it is. Not 100. The possibility is 1. I agree with this one. And I also did a lot of surveys. And all the people agree the second one. Now, until now, we have 2 events. And one event is, it is just 100. Second is not 100, no matter what it is. And now we have two events. And now the two events have the same possibility degree, or 1. That is exactly 100 is as possible as not 100. Do you believe? Now, if we have a gamble, now, do you want bet on exactly 100? You want? But anyway, compared with not 100, exactly 100 is almost impossible, right? If you don't agree with me, then we may bet. And you bet on exactly 100. I bet on not 100. Do you want? No one wants to do so, because all of us know that compared with not 100, exactly 100 is impossible. And now we have 3 conclusions. If we don't agree with the first one and third one, that is the first sentence is wrong. In other words, the strings is not fuzzy. And now, if we model anything by fuzzy set, then we may get such a paradox, and we may get some result that are counterintuitive. Also, fuzzy set theory is not self-consistent, and usually we have 2 important concepts. One concept of fuzzy theory is Zada's membership function, and another arbitrary law is extension principle of Zada. And all of us read many books related to fuzzy set theory, but we can't find any proof of this one. No proof. Because some people may think that it is a principle, not a theorem. And if you think it is a principle, or you think it is an axiom, then you should prove that extension principle is consistent with others. But we can't, because until now I believe that it is impossible to invent a mathematical system that contains not only membership function but extension principle. Impossible. And maybe it's difficult for me to prove it in such a short time, but I may give a simple example. Now, here is a membership function. It is a fuzzy set. And what value the fuzzy set take? And all the people think that the fuzzy set will take the alpha class. And now, here, we suppose that the membership function is continuous. And then the alpha cut is an interval, and closed interval. That is, it's a closed set. And now, what is the complement of this fuzzy set? It's also it's another fuzzy set whose membership function is 1 minus this one. That is like this form. And it's another fuzzy set. It also takes values of alpha class. What's the alpha class? This one. And usually it is a union of 2 closed intervals. But anyway, it is a closed set. Now, the the original one, its value is closed side. Complement, its value is also closed side. As a mathematician, you agree or not? And in classical set theory, the complement of closed side is open, and the complement of open side is closed. And here, the set itself is closed, and its complement is also closed. This means fuzzy set theory is inconsistent with the classical set theory. And usually, if this happens, we will think that this theory is not acceptable. That's why fuzzy set theory was criticized by so many mathematicians. That's the main problem. Now, what theory is acceptable? I think we should have two conditions. One is the theory itself is consistent, and the second is we can find a problem for which your method is the best one. Now, I think that in order to model indeterminates, we have two mathematical systems. One is probability, another is uncertainty. Now, let's check them by this principle. That is, probability theory is consistent. That's no problem. Mathematically, no problem. And second, we may find the example at which probability is the best one. For example, we toss a dice. Probability is the best one. And second, for the fuzzy set theory, from the mathematical viewpoint, it is inconsistent. That is, there is some contradiction in it. So, it is not consistent. This is first. Second, until now, we can't find any problem at which fuzzy set theory is best. Because fuzzy set theory may be better than probability, but uncertainty may do as well as fuzzy set. And the third one, until now we think that uncertainty theory is consistent, and we may find some example for which uncertainty is the best one. Perhaps some people want to know what is the difference between uncertainty and probability. And let's recall that probability is based on based on three axioms. And the first one is the probability of the universal set is 1. And the second is the probability of any event is non-negative. And the third one is additivity. That is, we get two events, and then the probability of the union is the sum of each one. And from the three axioms, and we may get the product probability. That is, now we have two events, and then the probability of the joint event is the product. Just like, one event is you come to this lecture room with probability 0.7, and I come to this room with probability 0.8, and then what is the probability that both of us come to here? It is 0.7 times 0.8. It is 0.56. And if we follow this system, then it is the probability. Now, for uncertainty, the first axiom is the measure of the universal set is 1. And the second one is duality. That is, for any event, the measure of the event plus the measure of its negation is just 1. Just like you may ask me, and I will invite you have lunch. You may say, what's the possibility, or what's the truth degree? I'm telling you, 0.8. And in this case, I mean, I will not invite you have lunch with truth degree 0.2. That is, if the measure of some event is 0.8, then the measure of its negation is 0.2. And anyway, the sum should be 1. And for probability measure, it is so. But for possibility measure, no. And usually, we want that some possibility, for example, we may do some fuzzy optimization, and we hope that the possibility of some constraints is hold with some confidence alpha, for example, 0.8. Now, let's see. Usually, we hope that here, in fuzzy optimization, we may hope that the possibility, for example, g, x, and we also have fuzzy numbers. And we hope that this constraint is greater than 0, and the possibility is greater than alpha. For example, is 0.8. And then we may get some result. And in this case, do you know this one? Gx xi less than 0. We hope that the constraints hold with confidence 0.8. What is the possibility that this one is less than 0? Some people think that, it's 0. No, you are wrong. And in this case, the possibility is 1. Sometimes we hope that the constraints may hold with confidence level alpha. But in fact, the constraint doesn't hold with possibility 1. So, duality is very important. And no matter, if we say the possibility is 0.8, then I mean that the impossibility should be 0.2. And no matter what the possibility is. And the third axiom is that sub-additivity. That is, now I give you 2 events. Then the measure of the union is less than the sum. That is the third one. And from these 3 axioms, we may define the set function. That is uncertain measure. And also, we need the product measure. And the product measure is the measure of the joint event is the minimum one. So, the main difference between uncertainty and probability is that the product measure is different. That is, if we take the product, then it is a probability. If we take the minimum, then it is uncertainty. This is the difference between uncertainty and the probability. And second one, what is the difference between uncertainty and fuzziness? Now, uncertainty assumes, probability theory assumes that the probability of the union is the maximum for any events, independent or not. But uncertainty theory, we assume that the measure of the union is the maximum only for independent events. And we did a lot of surveys, including many fuzzy experts. And you may read their papers. You will find that they only got the result, the measure of the union is the maximum for independent events, but maybe this one is overused or abused. If we assume this one for any events, then a lot of surveys show that human thinking does not meet it. And second, this is the reason why exactly 100 be as possible as not 100. So the main difference between uncertainty and fuzziness is that fuzziness assumes that the measure of the union is the maximum for any events, and for uncertainty theory, we assume that the measure of the union is the maximum for independent events. Please.
May I ask you that go back one side, please?
Okay. This page?
No, not.
Oh.
Only one. It's okay. Here in your there is when you make the union, there on the other side is the sum value.
Which one?
Here is the sum value.
This?
The third axiom.
This third?
Yes, and how it comes, this theorem that is for the independency.
Yeah.
I don't see.
And here, because this is for any events, not independent.
Not independent.
Yeah.
For all events.
Yeah, all events.
And then you go to the next slide, please. Then.
Yeah.
Oh, next. Next.
I don't know how to use this one. This page?
There is the union should be maximum value.
Yeah.
Value.
And I mean, possibility theory,
Yes.
assume it for any events, and uncertainty theory assume it for independent events.
Independent event, and this comes from your axioms.
Oh no. And this is a conclusion. And I got this result from the axioms.
Oh yes. I see.
Yes.
Sorry.
Yeah. And this one is almost axiom of fuzzy theory.
Yes.
Yes. Yeah.
But the other
It's all.
surprisingly.
Yeah.
This is how it comes from
Yeah.
axioms.
Yeah. It's almost time. And lastly, now as a conclusion, if we have samples enough, and then we may get the frequency, and then we may find a red curve that is close enough to the frequency. And in this case, we will regard this one as a probability distribution. And then, in this case, we have no choice but use the probability. And if we have no samples, then we don't know the frequency. And in this case, we should invite some expert to give some belief degrees. And in this case, we can't regard it as probability distribution because this may lead to counterintuitive result. And in this case, perhaps we have no choice but use uncertainty theory. And I think in such a short time, I can't explain it very well. And if you are interested, and you may download a book from my website. Okay, thank you. I think